Hi, welcome back to Mathematical Logic. We're going to talk about first order logic in this lecture. So one of the limitations of propositional logic is that it lacks the expressiveness to convey certain kinds of knowledge. Let me give you an example. So here's an example of a reasoning that at this point we can't really express with propositional logic. Any friend of mine is a friend of John. Peter is not John's friend, therefore Peter is not Martin's friend. So again, you can look at that again carefully and see that that's a reasonable deduction, but we can't really convey these ideas in propositional logic. Here's another example. All human beings are rational. Some animals are human beings, therefore some animals are rational. Here's another one. The successor of an even integer is odd. 2 is an even integer, therefore the successor of 2 is odd. And so here the problem is that we have some of the ideas that is not in propositional logic include things like any or some or all. Some of these ideas are not there, so we need to kind of add more concepts, more symbols to propositional logic so that we can get more expressive power. So one way to do this is to add something called quantifiers. So in order to make the structure of our sentences more transparent, we want to just kind of introduce some notation that we use frequently, and then we'll formalize them a little bit later. So when you have, so we're going to say P of X is going to denote the idea that X has the property P. So X is some object that has a property called P. So P of X means that X has that property. And then for all X, P of X means that this property P holds for all X. In other words, everything has the property P. So this means for all X, P of X. That means everybody, for everyone in our domain of interest, that person has this property. So everyone has that property. So we say for all X, P of X. And then here's another idea that we use, that maybe we want to say that some object has a certain property. So we're going to say there exists X. So we're going to say there exists X. P of X means that some X has the property P. That means at least one object has this property P. So this right here, for all X, P of X means that everyone has a property. This means there's at least one object that has the property. And so for all X here, this symbol in parentheses here, the for all X, this is called the universal quantifier. And then there exists X. This is the existential quantifier. Okay, so see how we can use those two new symbols to express the ideas that we saw in the previous examples. So this is any friend of John. Martin is a friend of John. Peter's not John's friend, therefore Peter is not Martin's friend. So let's come up with some symbol. So we're going to say f of xy here. We're going to say that this is going to mean, this is we're going to say later, this is called a predicate when we formalize this later. But a predicate is simply expresses a relationship between objects. So f of x comma y, this predicate that takes two arguments, x and y, means that x is a friend of y. Right? So later we see that the predicate can have many arguments, maybe one more argument, two arguments, three arguments, etc. But here's an example of a relationship where two people are friends. And then these names, these are constants, so we would denote them by M, J, P for Martin, John, and Peter. So these are constants, represent those specific objects. So here's how we can denote this this kind of reasoning. For all X, f of xm implies f of xj. So this says that for everyone, for example, say our domain is humans, for everybody involved, for all humans, if x is a friend of mine, so f of xm, then x is a friend of John. So that's how we denote, this line denotes this first sentence. If you're a friend of mine, then you're a friend of John. So notice we have propositional logic, and now we have some extra symbol that give us more power to express these ideas. Peter is not John's friend. Well, we'll just say that not f of pj. F of pj means Peter is a friend of John, so that's not true. And then this line means that therefore or hence. So if these are true, then the conclusion is that Peter is not Martin's friend. And so these are the premises, and this is the conclusion, or the entailment. This is the entail sentence from these two sentences. Okay, how about this one? All human beings are rational. Some animals are human beings. Therefore, some animals are rational. So let's say H, R, and A would denote those properties of being human, rational, and animal, respectively. These are again predicates. Notice these predicates are called one-place predicate, meaning it takes one argument. Notice earlier we saw that F is a two-place predicate. It takes two arguments. And so for all X, if X is a human, then X is rational. There's at least one X. There's at least one animal, one object, X, such that X is an animal and X is human. So that's the second sentence. And then finally the hence part, some animals are rational. I mean that there exists an X such that X is an animal, so A of X, and X is rational, R of X. So these three sentences correspond to these three. Notice now we can express this with more with the great ability to express more ideas. Here's another one. Successor of an integer is odd. 2 is an even integer, therefore the successor of 2 is odd. So this I is going to be for integer, E is for even, D is for odd, and S of X. We're going to call this as a function. So given an X, S of X gives you another number. So this is called the successor of X. So notice we will distinguish between predicate and function later. But notice S of X is a little bit different than the previous ideas of H of X, R of X. Those are relationship or properties. But S of X is called a function. Again, we'll make this precise later. So B is going to be a constant. Just like earlier we have Peter, John. B is going to denote the number 2 as a constant. So here's the successor of any even integer is odd. Says that for all X, if X is an integer and X is even, then the successor of X, S of X, is odd, D of S of X, where S is the function and D is the predicate that represent being odd. And then 2 is an even integer, means that I of B is an integer, and E of B, meaning that B is even. And finally, the successor of 2 is odd, means that S of B, successor of B, is odd, D of S of B. So this is some example of something called first order logic, where we take propositional logic and we kind of add more symbols to kind of give it more power to express ideas. Okay, here's some guidelines that might be helpful. So when you have things like all A's are B's, we say we use for all X, and we use the for all along with the connective, the conditional connective. By the way, I guess I will change my slides so that I should use the one arrow instead of the double arrow to make it consistent with the rest of the lectures here. But so I'll change that later. And so again, when you say all A's are B's, we want to use the for all, and we want to use the conditional. It says that for all X, if A of X then implies B of X. That means that for every object, if the object is in A, has the property A, the object has property B. That's the same thing as saying all A's are B's. For example, every mathematician loves music. You can translate it as for all X, M of X. If X is a mathematician, implies that X must love music. And the sentence some A's are B's can be expressed using the existential quantifier. There exists an X such that A, X, and BX. Some A's are B means that there's at least one X such that is both has property A and has property B. For example, some New Yorkers are friendly, means that there exists an X such that N of X, X is a New Yorker, and F of X, X is friendly. And finally, no A's or B's means that you do this. You do for all x, if x has the property A, then x does not have the property B. So no A's or B's. So for example, no philosopher understands politics. For all x, if x is a philosopher, then x does not understand politics. So again, these are kind of tricky. So you want to, if you haven't done this before, you want to kind of think about this very carefully. Read over these examples. Make sure you understand why we use these connectives. So typically we place the for all with the conditional connective, and we usually place the they exist with the and connective. Those go together. In the homework, we'll look at why we don't mix them. For example, if I put for all with an and, it makes it too powerful. And if I put the they exist with the conditional, it makes it too weak. So usually this is how we pair these up. By the way, there's no way a way of doing this. No A's or B's. We can also do it this way. We can say that there does not exist an x such that p of x and u of x. So this sentence and this sentence is equivalent, as we see in the next lecture. Okay, so yeah, make sure you understand that these two are actually the same, equivalent, and they express this idea: no A's or B's. Okay, let's do something more complicated. Some people respect everyone. We'll let p of x be x is a person. All of x, y. This is another predicate. This is one place predicate. Two place predicate. Mean x respects y. So we can translate this sentence: some people respect everyone as there exists x, right? Some means there exists at least one person. There exists an x such that p of x and, so p of x means that that x is a person, so there exists at least one person. And for all y, for anyone else, if that person is if that object is a person, p of y implies x respects y. So notice all the parentheses where everything lies. These two right here is connected by an and is inside these parentheses. Okay, make sure I didn't have any extra parentheses here. This goes. Yeah, I think that's good. Okay, so here's some recap, some symbols that we just introduced. So again, we have the same symbols as before: connectives in propositional logic. We have now quantifiers, existential and universal. We have variables now, like x1, x2, right? These are variables that represent objects in our domain of interest. Usually we just, instead of saying x1, x2, we say x, y, z. We have constants, a1, a2, an, or sometimes we say a, b, c. These are specific objects like Peter, John, or the number 2. We're gonna have so let's talk about predicate letters. So these are so the notation here is a of nk. So n tells you the number of arguments. If you take for example two arguments or one argument, and k is just to distinguish between different predicates. And so, but usually we instead of using this notation, we just say a, b, c instead of using the k as a subscript. And then the n, we use the function notation with n arguments. But these are predicate letters. And we also have function letters. We saw, for example, a predicate letter can include things like, if I go back to the previous example, p of x, right, this is a predicate letter. All of x, y, this is another predicate letters. They usually denote a relationship between objects. And then what are functions? Functions, again, same notation. The k used to distinguish different functions. The n tells you how many arguments it takes. And usually instead of using this notation, we make it simple by saying f, g, and h. Those are, instead of using the k, we just use different names for different functions. So capitalize A, B, C represent predicate for relationship between objects, and then functions f, g, and h. So these are the new symbols that we have in this new language that we're gonna formalize. So for example, x plays a role of variable in the previous example. For example, m, j, p, b, those are constants. For example, John, Peter, Martin, and b is the number 2. These are constants. F was a binary predicate letter. You remember F was the friend relationship. F of x, y, binary because it takes 2 arguments. So that's a predicate letter. And then we also have these monadic predicate letters, or predicate letters that takes only 1 argument. So for example, human, rational, even, odd, these are all the predicate, but they take only one argument. And we saw one example of a function s of x, for example, and that's a function letter. When we later talk about interpretation, then we will kind of distinguish these more, different between predicate and functions. But really, predicate actually form the basis. If you remember in propositional logic, the propositional letters like A, B that represent certain proposition, those are kind of the equivalent of predicate letters. Predicate letters have truth, false value. So that's way to think about predicates. And functions is just a mapping that maps an object to another object, or maybe more than tuples of objects to an object. So when we talk about interpretation later, we'll see why these are different. Okay, let's talk about terms. So this is one way to see why they're different. When functions and terms. What are terms? Well, variables, constants, those are terms. So those are the smallest units of terms. Another way to get term is to apply a function, again, an n-tuple function to a term. So if these are terms, t1 to, again, these could be constants or variables. Apply f to it, you get another term. An expression is a term if it's formed by one of these, by either one or two, or combining them or composing them. Term correspond to like nouns or noun phrases. For example, 2 plus 3, 2 plus x. Those would be terms, or Mike, John. So those would be the terms of the language. Okay, predicates and well-formed formulas. So when you take predicate letters and you apply them to terms, you get an atomic formulas. So this is kind of like a sentence back in propositional logic, or a formula back in propositional logic. So you have a predicate, you apply it to a term, then you get an atomic formula. And an atomic formula can have, truth, false values. So these forms the kind of the basis of all of our statements in our or formulas, right, in our language. So well-formed formulas of this. So this is called quantification theory that use quantifiers, are defined as follows. Every atomic formula is a well-formed formula. So for example, applying predicate to terms, that's a well-formed formula. And then if you have B and C well-formed formulas, you can create more well-formed formulas and Y is a variable by using the connectives, right? Not B, B implies C, etc. Or the quantifier, there exists x b for all x b. So once you create a basic atomic formula, you can create more formulas by using our connectives and using the there exists and for all. Just like we saw in propositional logic, once you have a basic statement letter, you can combine them to get more complicated statement letters. And so well-formed formulas would be the analog of that. So the expression is a well-formed formula if it's a combination of one or two. And then for all x, b, we say that b is the scope of the quantifier for all x. That's just so for all x, b, the b is the scope of the quantifier for all x. Parentheses. Parentheses can be used to clarify order of operations. Without parentheses, though, this is the order operation. You want to do not and or first, then comes the quantifiers, then comes the conditional and the biconditional. So in other words, the quantifiers goes in between here, right? Between after the negation and or, but before the conditional and biconditional. And then with connectives of the same kind, like if you have a bunch of or, you go left to right. But you have consecutive negations and quantifications, like negation and for all that exists, we want to go from right to left. So let's maybe we see some example here. Okay, so here's an example of a well-formed formula. So let's put parentheses to make sure we know what it means. Okay, so let's add some parentheses to clarify this. So notice in the first step, for all goes before conditional. So that means that this right here, we can put parentheses over here to denote that this is one unit. And then we can put another parentheses to say that the whole thing is one unit. So again, for all goes before the conditional. And this one right here, let's look at so here's the divisional statement. We add parentheses. Notice this parentheses goes between this one and that one. That's because the OR goes before the for all, right? The order of operation. Not and or goes before, has a higher order than the quantifiers. We can add another one to close it. And then this one right here, we want to go. You have a series of not. There exists not and for all. We want to go from right to left. Notice this is right to left. So that we have parentheses here to denote that they exist. So this whole thing is 1 unit. Then we have another parentheses here to denote that the not goes next, and then another one to denote that the for all goes next. So it's the exist is first, the negation, and then the for all. You go right to left. So when you have a variable x in a well-formed formula B, then x, we say that x is bound if either x is in the quantifier or it's in the scope of the quantifier. So we call that x is bound if it's one of those is true. Otherwise, x is a free variable. So for example, in this example, x1 would be an example of a free variable. It's not part of the for all. It's not part of the scope of a for all. And then in example number 2, x1 is free in the first part of the formula. Now this x1 is free, but this x1 is bound, right? This is the second occurrence of x1, and this x1 is also bound. So x1 is free here, but x1 here and here, the second and the third, those are bound. And then in example 3, x1 here is bound. So is this x1 is bound because it's in the scope of this for all, and this x1 is also bound. This x1 is also bound because it's in the scope. This one is inside the quantifier. So all x1 here are all bound. And then in example 4, x1 here is bound, and so is this x1. But notice that in all 4 cases, x2 is free. x2 is free here, x2 is free here, x2 is free here, x2 is free here also. Now notice x2 is not in the scope of this they exist x1. So x2 is free everywhere. Okay, so let's talk about a first order language. Now we can formalize everything. So first order language L contains symbols. What are the symbols? Well, we saw earlier, connectives, universal and existential quantifiers. All these variables form the symbols also. We want these to be countably many. Again, you don't know what countably means. It's one-to-one corresponds with the natural numbers, but so that's fine. These are variables. And then the function letters, it could be a finite or countably infinite, or even empty. So you don't have to have functions in the first order language. Constants, again, it could be finite, or it could be countably many, or it could be empty. Again, you can have them or you don't have to have them. But the predicate letters, though, you must have them. So the letters has to be non-empty instead of predicate letters, because without the predicate letters, you don't have any well-formed formulas. Remember, in the well-formed formula definition, you need to have that. Just like when you have propositional logic, if you don't have letters like A to represent it is raining, if you don't have those letters, then you don't have any logic. So predicate letters are the analog of those atomic formulas that we saw in propositional logic. Yeah, and so generate terms and well-formed formulas that we saw earlier, and then that all this is called the first order language. For example, in arithmetic, this is an example of first order language. What are the functions? The functions are things like addition and multiplications. Those are functions. Those are binary or two-place function. And then what are the variables? Well, we use x, y, z for variables. What are the constants? Like 3 would be a constant, for example, 5, 100. What is an example of a predicate letter? Inequality or equality in this case, for example, would be an example of a so how things are related. Is x equal to y? Is x less than equal to y? Greater than equal to? Less than? All those would be example of predicate letters, short relationships between objects. Yeah, so that would be an example of first order language. Now, first order language is still very abstract. All of them could be just letters, right? Predicates, function letters, all those are just letters. They don't have any interpretation. So we want to interpret the first order language. So for example, arithmetic would be a language, but also has an interpretation. right? Adding numbers, subtracting numbers, so the less than or equal to, those are interpretation of the language. So you have a first order language. M is the interpretation of that language. What does that mean to be an interpretation? Well, you need first of all a domain, the objects you're interested in. This is the D domain set, the domain of your interpretation. For example, we want to understand we want to understand integers. So arithmetic would be on integers. We want to understand maybe humans. Maybe our logic has to do with humans. So that's the domain. So we have to have a non-empty set called the domain. And then we have to have predicate letters. They have to represent something, right? We have to interpret these predicate letters. And so, again, predicate letters can take n arguments. And so for one interpretation, the way we interpret this is to say that predicate letters represent a subset of D of n, where D of n is just a set of n tuples of elements of D, and a predicate is just a subset of that. And so a predicate tells you how things are related, and that's why we have this tuple, right? If n is 2, for example, x comma y, x and y are related in some way. So a subset of that tells you the relationship between all these objects. Notice, right, D is the object, set of objects, and subsets represent how they're related. So for example, maybe we want to have a two-place, where n is 2, a two-place relationship. So if D is a set of humans, then maybe x comma y could represent a relationship of father of. So for example, x comma y means that x is the father of y. So you have a subset xy of D square, then that subset will show you the relationship between fathers and sons, right? For xy, for example. So predicate is tells you relationship, and mathematically it's a subset of D of n. So in this case, n is 2, D of 2 is a subset of all xy, where x could be and y are elements of D. And by having a predicate, we talk about a subset of that. So because not everyone is the father of someone else, and so when you have a subset, that can represent something like relation, right? Father of, or something, or less than or equal to, or less than. Those are predicate letters. Functions, a function from Dn to D. If you have a function of n arguments, then it takes the object and send it to another object. So that's how you think about functions. Is that the domain is could be n tuples of from the D domain, and then the output is in D. So those are functions, just like in math function. For example, if D represents the set of all real numbers, here's an example of a two-place function. It takes 2 input and then it subtract them. So the domain here is D squared, D2, and the output is D. Okay, this is another object in the domain. Okay, so given an interpretation of a language, if you have a well-formed formula without free variables, called a sentence, just like sentence in propositional logic, this would be a sentence in first-order language. So if you have a well-formed formula without free variables, then it basically represents a proposition that is either true or false. Whereas if you have a well-formed formula that has free variables, then that sentence can be satisfied or is true. So that's a misspelling here. For some values in the domain, because some variables are free, right? For some of those variables, if we pick certain domain elements, then that could be true. Or if for other objects that represent those free variables, it could be false. So yeah, so make sure you understand that. So let's see some more example. So if my domain is animals, maybe f of x represent x is a frog, g of x represent x is green. So those are predicate letters. So frogs are green, for example. Well, we can write this as for all x, if x is a frog, x is green. So again, for all goes with the connective, conditional connective. There's at least one green frog. Well, there's an x such that f of x and g of x. So now we notice we have an interpretation, right? Because f of x and g of x could represent anything you want. In this case, we interpret as being a frog and being green. And then our domain x is animal. So again, we can really this statement is a first order language, but when you interpret it, then it becomes there's an interpretation to the language. And of course, for any language, you can have multiple interpretations. Right? F could represent something else, for example. Right? Some frogs are not green. Well, that means that there's an x such that f of x and not g of x. So that there's some frog that is, there's some object that is a frog and not green. not everything that is a frog is green. It says that it's not true that for all x, if x is a frog, means x is green. So not everything that is a frog is green. This turns out to be equivalent to C. Turns out D is the same thing as C. This is the same thing as saying some frogs are not green. So again, later we'll see why this is true. But so make sure you understand that C and D are equivalent. There aren't any green frogs. So for all x, if x is frog, implies that x is not green. So that means that it's not possible to have any green frogs. If something is a frog, it's not green. No frogs are green. It says that it's not true that they exist in x such that x is a frog and x is green. So again, make sure you look at this again, but it turns out that E and F are actually equivalent. For all and negation of they exist, these are equivalent. So make sure you understand that. Here's another example. Humans. The domain is all humans. So maybe A, B, C represent Alex, Bob, and Kathy. So these are the objects or the constants. M and N, these are one place predicates. So M is a mechanic. N is for nurse. L is a two-place predicate. Again, these are just relationship, right? Or properties. Likes, so maybe one person like another person. So this is a two-place predicate. So for example, a mechanic likes Bob. So there's this in X. So again, X is human, such that M of X, X is a mechanic, and X likes B. B is Bob. So notice that this is L is a two-place predicate. It's a relationship between two objects, and M is a one-place predicate. So that usually represents some kind of properties. Where X is a mechanic, for example. Every mechanic likes Bob. For all X, if X is a mechanic, then X likes Bob. Some mechanics likes every nurse. There's an X such that M of X, and for all Y, if Y is a nurse, then X likes Y. So that's the same thing as every mechanic likes. Some mechanic likes every nurse. There exists one mechanic, and that mechanic likes every nurse. Yeah. So again, these are more examples of how to express these ideas in first order logic, and then these constants and these are interpretation of the language, and you need a domain. Okay, here's another example. So here, say we have these constants: George Bush, Bill Clinton, U.S. presidents. So these are constant. This is a one-place predicate. S is a one-place predicate also. Saxophone players. M is male. So for example, so now let's talk about when you have an interpretation. Then you can talk about things being true or false. Once you have an interpretation, you can say, oh, this statement is true in this interpretation. This statement is false in that interpretation. So for example, if this is our interpretation for all x, P of x implies S of x. So this says that, for all x, if x is a president, then x is a saxophone player. Well, it turns out that in this interpretation, this is a false statement, because there are some presidents who are not saxophone players. For example, George Bush. So notice this is now, again, this could mean anything in any interpretation. It could be about prime numbers or something, for example. But if I interpret this as humans and like people and presidents, then this might have a true or false value based on that interpretation. Here's another one. There exists an X is that X is not a president and X is male. Yeah, this is true, because in the case of all humans, there are definitely some humans that are male who are not president. For example, I am an example of a human who is not a president. And so notice again, interpretation gives you truth or false value. Now, of course, so this is the end of the lecture. In the next video, we'll talk about how to actually make inferences, and so in other words, if you have a bunch of statements, a bunch of formulas like this, how do you combine them, and how do you get entailment? How do you derive conclusions? How do you do inferences? Things like that. Okay, thanks for watching.